So in this hour, we are going to talk about the symmetric matrices. So it's like what we said on the handout that from now on, we only focus on the symmetric matrices because there are just too many things that is so great compared to other matrices. Symmetric matrices can be diagonalizable, the eigenvalues are real, and you can talk about the eigenvalue being positive or negative. We will briefly go through all these properties in this hour to show you that symmetric matrices are just great. Okay, so in fact, in the next 4 lectures, we will focus on lots of theorems that only applies to symmetric matrices. And in the first one, we are going to talk about inertia and congruent. So to make sure we are on the same boat, symmetric just means A is equal to A transpose. On the other side, you can talk about Hermitian. Hermitian means that A is the same as A star, and here star means the conjugate transpose. And so from now on, we will focus on the real symmetric matrices. But if you wish, you can also apply most of them to the complex Hermitian matrices. They are basically the same. But most of the time, we have a better picture of the real numbers. So let's not bother to look at the complex number. Okay, so the first theorem that I want to emphasize is the spectral theorem. And different book has different name for that. But I believe you have heard of this previously. It is kind of the fundamental theorem for symmetric matrices. That A be a symmetric matrix. Okay, then A is diagonalizable, and you can write it as A is equal to Q D Q transpose, where Q is orthogonal and D is real and diagonal matrices. So that's what I meant. You see, when you do the diagonalization, Q is the one that talk about the eigenbasis. The column of Q store the vectors in the eigenvectors. It is a basis, and these bases are orthogonal or orthonormal. And therefore, when you do the Q inverse, you can just use the Q transpose. And the second thing is, it is real. The eigenvalues are real. So there are 2 key points here. First, it is not just diagonalizable. It can be diagonalizable by orthogonal matrix, and the eigenvalues are real. So equivalently, there exists an orthonormal eigenbasis which means they are orthogonal mutually, and also the norm is equal to 1. The length is equal to 1. And the real eigenvalues So again, the key is it is orthogonal or orthonormal, and you can make it as a real eigenvalue. So to make the connection, D is actually equal to lambda 1 up to lambda n, and Q is equal to the matrix whose columns are U1 up to UN. Okay, so in fact these two conditions are equivalent. So that's the nice part. Everything is diagonalizable and the eigenvalues are real. So we don't need to care about those complex eigenvalues. And more than that, real eigenvalues, it is on a straight line, right? So real numbers can be compared, their quantity can be compared. You know, this side is positive, this side is negative. This is the property that complex numbers does not have. So the nice thing is real numbers can compare. That is, you can say lambda 1 less than or equal to lambda 2 and up to lambda n. And you can also talk about what is positive and negative. You are not going to say I is greater than 0, right? This is just not making sense. So the idea of the inertia is try to count how many number of eigenvalues that are positive, negative, or 0. So that A be a symmetric matrix. And with the eigenvalues, anyway, ignore that. Okay. The inertia of A is a triple denoted by INER of A, and this triple composed of 3 numbers, 3 integers, and we usually write it as n plus, n minus, and n0. These are integers, and they are the number of positive eigenvalues, negative eigenvalues, and 0 eigenvalues, respectively. Okay, just a quick example that say A is equal to this one, and you know that one of the eigenvector is 1, 1, 1, it corresponding to the eigenvalue 3, and on the other side you also know that this matrix has nullity 2, which means that you got two null vectors, which is 0, minus 1, 1, and minus 1, 0, 1. These are the two eigenvectors corresponding to the eigenvalue 0. So the spectrum, the eigenvalues is equal to 0, 0, 3, right? So that means it has one positive and two zeros and no negative. So in this case, we got n plus is equal to 1, n0 is equal to 2, n minus is equal to 0. And the inertia of A is equal to 1, 0, and 2. So that's the idea, and quite simple, right? It is just counting the number of positive eigenvalues and so on. Now we are going to talk about how to obtain the inertia. Okay, one way to do so is really do the diagonalization, like what we did here. Try to identify the eigenvectors and try to find the eigenvalues. But as you know previously, finding the eigenvalues is not so easy. You have to solve the characteristic polynomial. Therefore, it is not an easy task. And even worse, sometimes it is not going to be precise. Numerically, 0 is not always equal to 0. It is hard to tell whether something is really equal to 0. So now we are going to provide some more way to provide an exact algorithm. Exact means precise, 精准的演算法。So before that, we say two symmetric matrices are congruent Let's define what is congruent. Say we have two matrices, A and B. They are congruent if there exists a matrix, an invertible matrix, let's call that Q. Okay, it has to be invertible, such that A is equal to Q, B, Q transpose. It doesn't matter where do you put the transpose. Okay. So here is some keys, some emphasis. Okay, usually if you do the similar, two matrices are similar if A is equal to Q inverse BQ, right? You notice that here is the inverse. But now, no matter whether Q is orthogonal or not, we still use the transpose. And all we need is Q is an invertible matrix. It is an invertible matrix. So let's give it a try. So for example, we can do 1, 1, 1, 1. This is A. And we also have 1, 0, 0, minus 1. This is B. If you multiply something, like you multiply the matrix like this, and then do the transpose on the other side. Okay, so let's call this as Q. This is Q transpose. And then you can do the calculation. In fact, this matrix is doing the row operation. So after that, this 2 will becomes like this. So sorry, I wrote it wrong. And after that, you can multiply this matrix with Q, and Q is again the column operation. When you multiply an elementary matrix in the end, then it is a column operation. And after that, you will realize that these two are the same. So A is congruent to B. Okay, so if this is okay, then like what I said before, let me formally write it down. You can start from A to do some row operations and column operations simultaneously. The first part, this matrix, Q transpose, what it does is try to multiply -1 for the first row. You take the first row and multiply by -1 and then add that to the second row. And for Q, if you multiply Q at the end, then it is doing the same thing. It is doing the column operation. It takes the first column and then use that to kill the second column. So by looking at this, you will see that after doing the operation, it is just becomes like the diagonal matrix looks like B. And the reason that we care about this congruent idea is because congruent does not change the inertia. And this is called the Sylvester's law of inertia. And the statement is simple. Congruent matrices have the same inertia. So as we see, A is equal to this one, but it is congruent to B is equal to a diagonal matrix. It is not so easy to look at A and just look at its eigenvalue. But compared to that, B eigenvalue is just equal to 1 and 0. So the inertia is equal to 1 positive, no negative, and 1 0. And using this, we know that inertia of A is going to be the same as inertia of B, and which is equal to 1 0 1. If you really calculate the eigenvalue, then you will get the same result. So the final remark is like the following. The first one, when you do the invertible matrix Q, every invertible matrix it is equal to E1, E2, up to EK. And it is a product of elementary matrices. So this is some basic linear algebra fact that if you think of invertible matrix and then keep doing the row operation, in the end it will become the identity matrix. So every operation corresponds to an elementary matrix. Therefore, you can write every invertible matrix as a sequence of elementary matrices. And you know elementary matrices, each of them corresponds to a row or column operations. So, congruent A is congruent to B if and only if B can be obtained from A by symmetric row and column operations. Which means if you do an operation to the rows, then you have to do the corresponding symmetric one on the columns. Just like what we did before, what we did is like you do this operation, then you also have to do this operation to the columns. So in that case, it is called symmetric. And they will also preserve the matrix as symmetric matrices. Now the last one, the second remark, by doing symmetric row and column operations, every matrix or every symmetric matrix is congruent to this standard form. You have lots of ones and lots of minus one and lots of zeros. So sometimes we write it as identity of order P minus identity of order Q and the zero matrix of order R. And in that case, the inertia is just equal to P and Q and R. Okay, so I will stop here and you can give a try, and if you need some more example, we can provide that in the next class. But we'll stop here.